welcome to another video lecture in the series. This will be section 6.4, part 2. And here I'm going to show you some of the basics about how to solve these linear difference equations. Very similar to solving linear differential equations. So if it looks familiar, it's because you've probably seen something very similar before. And we'll just go through enough of it to give you the idea of how to deal with a few of these cases, and then we'll be on our way. All right, let's get started. The next section is a tutorial on how to solve linear difference equations. So this will seem a lot like solving linear differential equations if you've seen them before. So there are many parallels if you're noticing. Let's start with equation 6.23, and that is the general form that you'll see of the linear difference equation for this section. It's essentially what you get if you apply an R-step linear multi-step method to that trivial IVP when you're trying to check zero stability. Now, assume that you've got all of these starting values. Then what do you do from here to try to solve this thing? Well, you do exactly what you do in sophomore linear differential equations class. You say, I'm looking for a solution of 6.23 of a certain form, and that form is the following. So you're looking for a UN that is of the form zeta to the power of n. All right, that's your solution form. Now, here is the big thing to pay attention to. On the left side, this n here, this n represents an iterate of your approximation scheme. So UN is still a time step counter for us, okay? The thing to keep track of is that over here on the other side, this n is actually a power. It's actually an exponent. This really is exactly how you think of it from algebra class. It's zeta raised to the power of n, where n is an integer, okay? So it's really important to understand this in context. So I make all kinds of little notes. Now, let's go back and think about what I just said. I'm looking for a solution of equation 6.23 of the form equation 6.24. Now, whenever you're looking for a solution of a certain form, what do? Well, you plug it into your equation, and then you see how you can simplify. In this case, I plug my zeta to the power of n in here, and so I see how I have this common power, if you like, at this point, which now is zeta to the power of n. So if you think about it this way, you can say, all right, well, this is really the same as zeta to the power of n factored out like so. Oops. So now what you see is that if I factor that zeta to the n out, then what I have is the product is equal to 0. This thing is not equal to 0 for all zeta, so we must have that this other piece must be 0, and that's how we get that expression right there. And now pay attention to the fact that this expression on the left side is simply rho of zeta, where that is your polynomial that we introduced way back in section 5.9.2. All right, so now here's the observation that you want to make. Here, zeta to the nth power is a solution of that difference equation if zeta satisfies this particular equation right here. That is this guy where that summation is set equal to 0. So in other words, zeta to the n is a solution of the difference equation if my zeta is a root of my row of zeta, which is my characteristic polynomial for that corresponding linear multistep method. So we'll do a couple of examples here shortly so you can see what I mean. In the meantime, the first thing to think about is, okay, if I'm looking for a root of a polynomial, what do? Ideal case. Well, if I can factor rho into this very snazzy form right here, then I can eyeball what the roots are. So assume that you can do that here. Assume you have factored rho of zeta and zeta sub I are distinct roots. Then what that means, if you go back up here, those are the roots which satisfy 6.25. Likewise, what that means is for each one of those roots, this corresponds to a zeta sub I raised to the nth power. That becomes a solution to my difference equation. All right, so there is a correspondence here. If I'm looking at roots of my polynomial, then I take those roots, raise them to the nth power. Those guys are solutions of my linear difference equation. And you'll just have to take it on faith here that if you have distinct roots of your polynomial, then these solutions form a linearly independent set of solutions to your difference equation. And this may seem also familiar to you. I can then generate a general solution to that difference equation, which is any linear combination where the C1 through the CR, those are arbitrary constants. This is my form of U superscript n, U to the power of n. Sorry, U superscript n. All right, so I have generated my solution, my general solution to my difference equation. How do I figure out what my initial conditions tell me about those starting values? Well, remember that these initial conditions say things like U1 is really, well, sorry, U0, that's my initial condition. This is the n equals 0 case, and I have a value for that. U1 is my n equals 1 case, and I assume I have a value for that, and so forth. So I assume all these guys will then satisfy that the UN that I see up here corresponds to these. So here is my n equals 0 case. Here is my n equals 1 case, and so forth. N equals 2 case, and so on. So just plugging in for different values of n and looking at what those corresponding equations look like. All right, so again, you're in this situation where the exponents on the left side here, oops, sorry. On the left side, those exponents are actual powers, right? These are standard exponents that you know about from algebra class. Over here on the other side, these exponents are your iterates. So this is my starting value at t0 equal to 0. This is my starting value at time step t1, which is simply 0 plus k, or t0 plus k, and so forth. Okay, so on the right side, these are iterate values, and on the left side, they're standard powers. Regardless, what can you do? Well, you can still solve a linear system. The stuff on the right side is given, and the stuff on the left side, the only unknowns are C1 through CR. What it all boils down to, as in many cases in applied mathematics, is a linear system of equations to solve. All right, what I want to do now is I want to take you back to that same example that we started with in the first video in part 1. Let's go back and look at that again for a minute. Let's use the machinery we've got now. So now I have a very particular characteristic polynomial. I have this guy, right? And I can eyeball that from this thing. Easily eyeballable. Hopefully that is pretty easy for you to see. And now, all right, I do a little high school algebra and I factor and I see what my roots are. And based on these roots, this means that my solution to my difference equation, my general solution, looks like this. Well, once I have that general solution, I have two starting values. Now, I just, for now, assume they're called U0 and U1. And now from here, if I actually plug into that same system that's above here, where I only have an n equals 0 and an n equals 1 case, then I see these two equations popping up. And what happens? Well, I can solve that for C1 and C2. And you can see where I've done that over here. Then from that, I can say that my U superscript n is simply, well, it's this guy with that C1 and C2 plugged in. It turns out that that's going to be given by this. Now, once you have looked at that, go back and look at that example that we started on in part 1 of these videos. That will hopefully help you see how we wound up getting this example or the solution for that example. I want to make a few observations. Notice this particular polynomial, well, if it has any roots where my zeta sub I are larger than 1, that method won't be convergent. Okay, and this is an example of that, right? Zeta 2 is 2, and we already talked about in the previous example how, in the previous video, how the thing can diverge from 0 as you move through larger and larger values of n. Okay, so if I have any root of my polynomial rho of zeta, which has absolute value or modulus greater than 1, then my method will not be convergent. If all the roots of that row of zeta, let's call them zeta sub I, if they all satisfy this, then you can see how you're going to get something which will converge to 0, right, as you increase n. Think about that in terms of this particular expression right there. As I allow n to increase, all of those zeta i's raised to a power of n are going to get very small and converge to the 0 function on the right-hand side. Okay, I have considered these two cases, the case where there's a root that's larger than 1, there's a root that's larger than 1, and there's the case where all the roots are smaller than 1 in magnitude. Well, now here's the special case. What happens if you have a case where at least one of the roots has a modulus or a magnitude or an absolute value of 1? Well, if that's the case, then that means that if the polynomial row has a repeated root where zeta 1 is equal to zeta 2, then these two expressions are not, they're not linearly independent anymore. They're not linearly independent solutions. They would be the same solution if we have a repeated root, okay? So in order to obtain two linearly independent solutions, this one you're just going to have to trust me on, you use this, okay? So if zeta 1 and zeta 2 were the same, then here's how the linear combination of roots raised to powers would work. Here is your original, and then here is your n times zeta 1 to the n power, okay? So those two expressions together form two linearly independent solutions, and here with the rest of this, I just assumed that all the rest of the roots were distinct, okay? So this is the kicker. This is the issue of where we have to be careful, okay? If we have a root which has modulus 1 or magnitude 1, and that happens to be a repeated root, then you have to deal with that a little more carefully in terms of solutions to your difference equation. All right. So here's what I'll say. At this point, if this seems a lot like solutions to linear ODEs, it's because it is. Thank you for watching, and in the next video, we'll check out an example.